Hey everyone, welcome to video number 1, lecture number 1. Today we are going to discuss molecular structure. In the next video, lecture 2, we will discuss formal charge and bonding. And the third video will be workshop number 1, where we practice these topics with practice problems. Okay, so this is the first video in the organic chemistry sequence. This sequence is going to cover all of organic chemistry from start to finish. So we'll start with very introductory material, go through the entirety of organic chemistry. So this sequence will help you if you are a student struggling through organic chemistry, or perhaps a medical student looking to do well on the MCATs, or simply just someone who's interested in learning more about organic chemistry. As long as you have a rudimentary understanding of chemistry, high school chemistry, maybe a general chemistry course, you should be perfectly fine to follow along throughout this lecture series. Okay, so let's go ahead and get started with our first lecture, lecture number 1. So for drawing molecular structures, how do we draw a structure? Well, in order to draw a structure, we need a formula. So I'm going to draw a formula here, a molecular formula, C2H6O. C2H6O. This is what we would call a molecular formula. It's a formula indicating what atoms are present in the molecule. So this is a relatively simple formula. We have 2 carbons, we have 6 hydrogens, and we have 1 oxygen. Obviously, this can become much more complex, but it could also become much more simple. Okay, we know very simple molecules. For instance, H2O is water, very simple molecular formula. Water is composed of 2 hydrogens and 1 oxygen. Or carbon monoxide, CO, 1 carbon, 1 oxygen. These are very simple molecular formulas, and obviously they can get very complicated very quickly. Okay. Now this is our first organic molecule that we're looking at, C2H6O. And so what does this mean? How do we draw a molecule from just these letters and numbers? Well, in order to do that, we need to sort of figure out what pieces of the puzzle do we have. So let's go over here to where I have this section drawn out, and we are going to quickly review Lewis dot structures. Remember, Lewis dot structures show the valence electrons for an atom. So Lewis dot structures will show you very precisely how different atoms participate in bonding. If we want to draw a Lewis dot structure for carbon, what we have to do is we have to look at the periodic table, and we have to simply count what column is, or what group is carbon in. Carbon is in group 4A. Okay, start at the left of the periodic table and work your way to the right. Carbon is in group 4A, so carbon has 4 valence electrons. Remember, for Lewis dot structures, you simply add 1 electron on each side of the atom. So down here on carbon, I added 1 electron on each side. It has 4 valence electrons, so we have 4 unpaired electrons. Okay. Nitrogen is in group 5A. 5A, so nitrogen has 5 valence electrons, which means one of those electrons is paired up with another one. So we'll have a pair of electrons. It doesn't matter where you put the pair, but we have 1 pair and then 3 single electrons. Oxygen is in group 6, so we will have 2 paired electrons and 2 unpaired electrons. Hydrogen is 1 electron, so it has 1 valence electron, easy enough. And the halogens, this would be chlorine, bromine, iodine, and fluorine, all have 7 electrons. So both hydrogen as well as the halogens are what we would call monovalent, meaning they participate by making 1 bond, monovalent. Okay. The halogens have 3 lone pairs associated with them, but at the end of the day, both hydrogen as well as the halogens have 1 single electron for bonding. Okay, so wherever we see a single electron, that's a spot we can make a chemical bond. That's a spot we can bond. Okay, so if we look at oxygen, oxygen is what we would call a divalent atom because it has 2 unpaired electrons, one on the right, one on the left. These 2 spots are where we could make a chemical bond. So oxygen can form 2 bonds. It also has 2 lone pairs, which will be important in future chemistry. But for now, we're just looking at bonding. We're looking at those single electrons. Oxygen can form 2 bonds. Nitrogen can form 3 bonds, trivalent. Nitrogen has 1 lone pair and 3 single electrons. Carbon is tetravalent, meaning we can form 4 bonds to carbon. A very common mistake that students will make is they will simply neglect these very basic rules for bonding. Okay, for instance, we might see carbon with 5 bonds. This is a common mistake, but it's very important not to forget these basic bonding rules, where hydrogens and halogens can form 1 bond, oxygens can form 2 bonds, nitrogen 3 bonds, carbon 4 bonds. And again, this all depends on the valence electrons of said atoms. Okay, so for example, we could go look at boron on the periodic table. Boron has 3 valence electrons. Okay, 1, 2, 3. So boron is also trivalent, but boron does not have the lone pair. Boron only has 3 valence electrons, 1, 2, 3. So boron would be trivalent. Now boron is much less common, and we will really not be looking too much at it. Organic chemistry is really going to be considered with these atoms here. Okay, CHON, CHON. This is what most organic chemistry is. We will see some halogens. We will see fluorine, chlorine, bromine, iodine. We will see things like silicone, phosphorus here and there. But most of organic chemistry will be carbon, nitrogen, oxygen, and hydrogen. So it's very important not to forget these basic rules of bonding. Okay? So these are essentially our puzzle pieces for putting together the puzzle, which is the structure of the molecule. Let's go back to our formula here, C2H6O. How do we put together a molecule using these atoms? We're going to start just by taking an atom of carbon. Let's draw it in red. I'm going to draw the valence electrons out like this. We have 4 valence electrons around this carbon. Now, when you're trying to determine a structure for organic chemistry, it's actually a good idea to ignore the hydrogens at first. Don't worry about the hydrogens. Hydrogens can only form 1 bond, so they can't really do anything interesting in terms of bonding. They are simply going to be on the ancillary positions of atoms. They'll be on the exterior. They're essentially going to fill in all the empty spots. Okay? So what we want to do when we are considering a structure is we want to look at the atoms that can participate in multiple bonding patterns. Anything that's di, tri, or tetravalent. These are the ones that are going to be interesting because the bonding patterns can change between them. They can form multiple bonds. Okay? So, just to summarize that, when you're drawing a structure from a formula, just forget about the hydrogens for now. Put them on at the end. It's much more simple. Let's draw another atom to connect this carbon to. Let's connect it to another carbon. I'll draw this one in blue. Now, again, where we are bonding is where we have 2 single electrons coming together. So in the case of these two carbons, we have one electron coming from the red carbon, one electron coming from the blue carbon to give us a 2-electron bond, a bond between these two carbons. Okay, so those two carbons are now bonded together. What about the oxygen? Let's add it on the very end over here. O has 2 lone pairs and 2 single bonds. One is bonded to this carbon. And now we have 1, 2, 3, 4, 5, 6 hydrogens, and we have 6 single electrons. So at the very end, we're just going to go around and fill in all the empty spots here with hydrogen. Just fill in all these empty spots. Now, if you don't have the right number, it means you messed up somewhere. We have 6 single unpaired electrons. We have 6 hydrogens. So we simply add them to each spot that's left over. If your hydrogens don't fill in, it means you missed something. You have the wrong number of carbon or oxygen, or maybe you drew them in the wrong way. Okay, so you should have 6 spots left over. Add a hydrogen to each spot, and we have drawn our first molecule. This is ethanol, or ethyl alcohol. Okay, this is what's commonly found in adult beverages. There's also many other uses for ethanol. It's a very common substance. You'll find it as a fuel additive, for example, among other things. Okay, so this is our first molecular structure, ethanol. Now, the first question that you always get at this point is, well, what if we put the oxygen in a different position? Why did we go CCO? What if we went like this? What if we took the oxygen, connected it to a carbon, and connected that to a carbon, and then we filled in with hydrogens to make this structure instead? What if we did this? Now I'm drawing lines here instead of a pair of electrons, because if the line is indicating a chemical bond, each line that I drew here is a pair of electrons that's bonding these two things together. So this line between the CH, that's indicating a pair of electrons that's bonding carbon and hydrogen together. One electron is coming from carbon, one electron is coming from hydrogen, and they're coming together to form this 2-electron bond. Okay, so you'll see it looks a little bit cleaner, a little bit more clear when we draw our chemical bonds as lines instead of as pairs of electrons. So what if we drew this structure instead, where we have oxygen on the left instead of the oxygen on the right? Okay, I'm also going to add in this lone pair on the top, this lone pair on the bottom for oxygen, just so that we have everything drawn out. So are these two structures the same? Are these structures the same, or are they different? These two structures are exactly the same. And if you can't see why that is, I want you to take a pen or pencil and put the tip of the pen or pencil facing to the right, and then flip the pen or pencil so it's facing to the left. You haven't changed the pencil in any way. It's not a new pencil, right? It's the exact same writing utensil, but you're just looking at it differently. You have a different perspective on it now. And that's exactly the case with these two molecules. If you can imagine taking this molecule where we have carbon, carbon, oxygen, and just flipping it like a pancake, flip it over. Now we have the oxygen over here on the left instead of the right, but it's the same molecule. We didn't draw a new molecule by drawing the oxygen on the left side. We've drawn the same molecule just from a different perspective. Okay, this is a very important concept that we will get to in more detail in a future chapter when we talk about three-dimensionality of molecules. But for drawing structures, it's important to understand and to think about whether or not you've drawn a unique new molecule or whether you've simply redrawn the same molecule from a different angle. And if you're ever confused and you don't know if it's the same thing or not, all you have to do is work down the chain, work down the backbone of the molecule. When I say backbone, I refer to the central atoms here that are participating in a lot of bonding. Typically, it's going to be carbons for organic chemistry. So if we work down this central backbone of the molecule here, we have carbon, carbon, and then oxygen. If we work down this backbone of the molecule down here, we have carbon, carbon, oxygen. It's the same order of atoms, the same connectivity of atoms. Okay, so these two are the same. So it doesn't matter if you draw the oxygen on the left, and it doesn't matter if you draw the oxygen on the right. What if you drew it like this? What if we took a carbon, connected it to a carbon, and then put the oxygen up like this? What if we did that? Is that the same, or is that a new molecule? This is also the same. All we've done in this other case here is we've drawn the oxygen going up from this carbon instead of to the right. But again, if you're ever concerned or confused, work your way down the backbone of the molecule. We still have carbon connected to oxygen. It's still the same molecule. What we have to consider here and what we have to remember is that molecules are moving around all the time. They're not rigid. Molecules can spin and stretch and flex and bend, and it's hard to represent that on a two-dimensional piece of paper. Okay, so once we get to the chapter where we'll talk about three-dimensionality in more detail, this will become more important. But for now, the key thing when you're drawing molecules and you're not sure if you've drawn the same molecule more than once, always just work your way down the backbone. Count what you have. We have carbon connected to oxygen. And in the other two molecules, again, we have carbon connected to oxygen. Okay, so all of these are the same molecule. All of these are ethanol, just drawn a little bit differently. Okay, but the connectivity is what's important. The connectivity is what matters. CCO, CCO, CCO. Okay. So we could draw another unique molecule using the same molecular formula here. What would that other molecule be? Well, let's draw a carbon to start. And instead of connecting this to a carbon, I'm going to connect it to the oxygen and then the carbon. Now, you should be able to see how the backbone of this molecule is different from the ethanol that we drew before. Okay, this is what we drew before, ethanol or ethyl alcohol. That backbone was CCO. The backbone of this molecule that we're drawing now could be COC. Okay, COC. Now, oxygen has 2 bonds and 2 lone pairs, so oxygen is all set. And we know that carbon is tetravalent. Carbon forms 4 bonds, okay? So over here, we need 3 hydrogens. And over here, we need 3 hydrogens, which works out perfectly because we have 6 left. 6 hydrogens, 1, 2, 3, 4, 5, 6. So we've drawn a new and unique molecule here that's different from the ethanol that we drew previously, okay? Again, this is ethanol. ethanol, eth meaning 2 carbons, and ol meaning it has an alcohol on it, an OH. We'll get to nomenclature more in the future and we'll practice it as we go, so don't worry too much about nomenclature. It should come naturally. Down here, we have an ether, which is a general functional group. When I say functional group, I just mean some connection, some general connection of atoms. An ether is when you have an oxygen with carbons on both sides. It could be any sorts of carbons, long carbon chains, short carbon chains, or just like we have here, 1 carbon. Okay, this would be specifically dimethyl ether. Dimethyl, methyl meaning CH3, and di meaning there's 2 of them. So this would be dimethyl ether. And up here we have ethanol. Now you should be able to see, again, why these are different. The backbone, the connectivity of these is different. We have CCO as opposed to COC. The connectivity is different, but they still have the same molecular formula. Both of these have the formula C2H6O. Okay, so what we call these is constitutional isomers. Okay, constitutional isomers. Ethanol and dimethyl ether are constitutional isomers because they have the same molecular formula, but different structure, different connectivity. They have a different constitution. So you might see the term constitutional isomers or structural isomers. Both of these terms simply mean same formula, but different connectivity, a different structure. Okay, so these are 2 constitutional isomers that we can draw from the molecular formula C2H6O. Okay, let's look at a different molecule here. Okay, let's look at a molecule. Let's say C2H4. C2H4. So how do we draw a molecular structure from the molecular formula C2H4? Okay, I always like to start by thinking about the building blocks that you have. We have two carbons and we have 4 hydrogens. So we need to plug all these together to make a structure. Again, when you're drawing a structure, start with your atoms that can have multiple bonds. Let's get that backbone drawn first. Let's bond carbon to carbon. Okay, carbon to carbon. We only have 2, so it's pretty straightforward. And then we have 4 hydrogens left. Okay, so let's add our 4 hydrogens around the outside. Let's go 1, 2, 3, and 4. Okay, so something's not right here because we have 2 unpaired electrons left over. Now, is the molecular formula wrong? No, it's not wrong. This is the correct molecular formula. What's going on here? We have a double bond between carbon and carbon. So we don't just have a single bond, but these 2 electrons up here, these 2 unpaired electrons, also hop down, make a bond, And we're going to put 2 lines in between these 2 carbons to represent a double bond. So we have 2 carbons that are double bonded to each other. And then each of those carbons has 2 hydrogens coming off of them. Remember, carbon should always have 4 bonds. This is where students can get confused once we start adding double bonds and triple bonds. Carbon will always have 4 bonds. Carbon, let's take a look at the carbon on the left. It has a double bond, 1, 2, and then has 2 hydrogens, 3, 4. So that checks out. That's good to go. And it also has an octet. That's another good rule to look at, good thing to think about. You should always have 8 electrons around each atom. Remember from high school and Gen Chem. This carbon has 8 electrons around it because it has 4 bonds around it. Each bond is composed of 2 electrons. Okay? So this carbon's happy with 4 bonds. This carbon is happy with 4 bonds. So we've drawn our structure, which is C2H4. Now, there are no constitutional isomers or structural isomers that we could draw using this molecular formula. This is the only way we could connect these atoms together. Now, you can imagine as we increase the complexity of the molecular formula, we increase exponentially the number of isomers that we could draw. Okay, but for these simple structures, for these simple molecular formulas, there's not going to be a whole lot of ways that we could connect them together. There's not going to be a whole lot of constitutional isomers to think about. Now, if we consider the structure C2H2, this is very similar. Let's connect these 2 carbons together, and we only have 2 hydrogens. 1, 2, which means we have 4 unpaired electrons. So we're going to combine those together to get a triple bond. That's going to give each carbon 4 bonds. If we do a triple bond between these 2 carbons, H connected to C, which is triple bonded to C, which is single bonded to H. Each carbon still has 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Still has an octet, still has 8 electrons around it, 8 electrons around it. So everyone's happy. And this would be the structure for C2H2. Again, that's the only way we could draw that structure. There's no other isomers that we could draw. And over here, C2H4. Okay, so we've seen a couple examples here where we've drawn molecular structures. We've looked at double bonds, we've looked at triple bonds, and these are things that we need to consider when we're drawing molecules in the future. The third video will be a workshop video where we can get much more practice on this. So if you want more practice and you're ready to go, check out video number 3. It should be titled Workshop 1. And this is where we'll practice drawing structures from formula and vice versa. Okay. Again, as we go through the course, things will come naturally to you. We will remember that hydrogen always forms 1 bond. Chlorine, bromine, iodine, the halogens will form 1 bond. Oxygen, when it's neutral, should have 2 lone pairs, 2 bonds. Nitrogen, when it's neutral, should have 1 lone pair and 3 bonds. Carbon, when it's neutral, should have 4 bonds. Okay. Next lecture, we're going to be looking at formal charges. So we're going to be adding some charges, either a positive charge or a negative charge to these structures. Okay. And we're also going to take a closer look at bonding, talk about different types of bonds, polar bonds, non-polar bonds, etc., which you should have been introduced to in high school chemistry, but if not, we're going to start from the beginning and work all the way through it. Okay, thanks for joining me for lecture number 1, and I will see you guys in the next one.